Welcome to our third video workshop, and this workshop is going to be measurements and layouts in the shop so you can build a chassis or any other component. And to do this, the first thing we need to do is learn about jigs. Now, what is a jig? Jig is a temporary structure that holds components in alignment so they can be fabricated and joined. That's all a jig is, and I'm going to show you how to construct one accurately, avoid stack up, that sort of thing. However, always in a shop environment, one, we never work alone. Two, we know where a phone is, or we have cell phones available to call 911 in case there's an incident. We know where a first aid kit, it is right on the wall. We know where fire extinguishers are, there they are on the wall. We attend to safety before we do anything else. Then we begin to work. So, first of all, you start with a drawing. It's created in SolidWorks, on a napkin, whatever. From that drawing, you have measurements. Those measurements have to be translated into metallic parts or composite parts or whatever, and they have to be converted into a three-dimensional part accurately to a tolerance area. Now, the tolerance area we like to see when we're building chassis is plus or minus 1 millimeter. Now, I don't see how long this is. This is an 8-foot long table. Here's this component. It's built to an accuracy of about half that, plus or minus half a millimeter, for a total error window 1 millimeter. But for your formula cars, your Baja cars, that sort of thing, we operate on plus or minus 1 millimeter. Now, we have to have some way of measuring that, so we have to have rulers. So, let's start out with a simple ruler. Here's the pocket ruler. This is the smallest, that would be considered accurate. It's a stainless steel ruler. It's etched with the lines in it. Rulers that have painted on lines, like this 3-foot yardstick here, you can see where they're worn away. This is a very inferior ruler. Avoid these if at all possible. You want to get the higher quality rulers that have etched in lines, because they don't move around and smear off, obviously. And plus, they're generally made to a much more accurate tolerance on the edge. So you can buy junk. Remember these from your elementary school days? Don't use them. Plastic crap, don't use them. The minimum you can use is a real certified drafting instrument. I'll allow that, and we'll allow that for accuracy, but that's as low as you can go on the food scale. We want to use real industrial rules that have high accuracy. Now, we should also talk about how to read one of these things. Of course, they're graduated in metric or SAE. However, there's something that creeps in to everything that's manufactured, and it's called tolerance stack. And tolerance stack, if I took this short ruler, I've got an 8-foot table, I started down at this end, measured off 6 inches, made a mark, moved the ruler, another mark, another mark, another mark, another mark. I will always be off a small amount each time I transition the ruler down the table. By the time I get to the end, I could be off 1/4 of an inch. That's tolerance stack. We want to avoid that. One way we avoid that is that we use accurate rules, 1. 2, we select rules to scale. For example, if I wanted to measure something this long, 1-piece ruler. Always the best way to do it. Using multiple rulers and trying to move it, kabunk, 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 tolerance stack, always. Now, if you have uneven surfaces to measure, something round, something oblong, this is a seamstress cloth ruler. They're subject to stretch. However, you can wrap it around things, get a reading, then translate that to a known accurate ruler. That's the way you do that. So if you got to measure something around, like your head or something like that, and you want an accurate reading, you translate whatever the reading is here to an accurate ruler. So that's a good little trick to know. Now, let's talk about pocket rules. Everyone's seen these. These actually, if you look on this table, we've actually taken inexpensive carpenter rules and permanently attached them along the edge. Screwed them down. That's good because we can start from one edge. These are all made by the same company, so they came off the same assembly line, and we pull two this way, and then we pull two this way. You don't start one end on one end and the other end on the other end. You always start them on the end. So that way, if I wanted to bridge all the way across this table, I can come down to 51 inches over on that rule, 51 inches on this rule. I've got a cross line 51 inches from that edge. And I can rely on that because that's going to be fairly accurate. Now, using these for all your measurements is not a good idea because you see the little catch on the end? It's made on rivets, and this is what messes up the final accuracy on these if you don't know how to use them. This thing is designed to slip out ever so slightly, about 1 millimeter, when you do this, and it pulls this way. This gives you a relatively, not really super accurate, but it gives you when you're pulling like this, it allows that line to more or less come fairly close. If you're trying to measure by butting it up against a wall, like this, it slides in and tries to correct for the thickness of the 90-degree catch. That's why it moves, is to try to correct for the thickness of the 90-degree catch, but it's not real accurate. So if you're going to use these, you want to be very particular and double check your measurement, measure twice, measure from this way, measure from this way, and make sure they agree. If they don't agree, then that's the error in these kind of rules, and you have to watch that. You're always better off using a long one-piece rule that will span the job you're trying to do, or to use separate measurements the least amount possible. So this is called a surface table, or a surface plate even. Now, it's nothing more. You can fabricate one of these for a fairly large project relatively inexpensively. This is a 4x8 sheet of aluminum. It's 1 millimeter thick. It's attached to a 1-inch thick piece of plywood. The 1-inch thick piece of plywood is mounted on a frame of 2x6s, mounted vertically, just like floor joists. So that way we get a nice, stiff, level bed. And if you notice the legs of this table, they're mounted in the corners for strength. They come down, and then you have these secondary blocks. The secondary blocks are for leveling it on the floor, because floors are not always very level. This room's especially horrible, so we have these secondary blocks. Once we establish the table level in this direction, we turn this, our big spirit level rather, perpendicular, and we leveled it this way. And to prevent sag, this is real important on these type of tables. I don't know if the camera can see it, but underneath we have a jack right in the center. The jack can lift and allow for any sag in the table. It's important that these tables be maintained in a level plane, because you cannot get a accurate vertical reference if the table is on a tilt. Once you get a level table, then you can do good, accurate work. Notice here, if the camera can see it on the floor, we actually painted around the feet of the legs so that if the table is jostled, and I did jostle it to show the paint mark here, you can tell and you can move the table back into position so that it goes back in register with the floor, and everything will work out properly there. So you have different length rules. You size that to the scale. In the drafting equipment, when you need angles, drafting angles are very, very good. If you need a 90-degree angle, these are very accurate. If you need a 45-degree angle, these are very, very accurate, 60-30, like that. For squaring, you need a square. This is a medium-sized one, and it's so you can scribe a line, draw a line for cutting that's perpendicular along the longitudinal axis of any material. And for longer measurements, we have longer versions of that square. Just like with the ruler, bigger and longer is better. And you can do a neat trick with these things, and I want to show you that. Getting the table level, getting rules attached to the edge of the table will give you a way to create X, Y coordinates on this table. So if I want the corner of this chassis structure to be so many inches in X and so many inches in Y, I could put a mark, lay metal down on that mark that I've measured out, and it will be accurate. And that's what a table is all about. However, we got to come up and create an upper level structure. So how do we get vertical? I'm going to show you how to do that. You need two of these. Place one this way, nestled against it, because although this edge sitting on a nice level table will be vertical, it will not be vertical in this plane. So you take a second one and you tee it. Now, this edge and this point is exactly above that point. And you can measure off this way, that way, wherever. You can use this as an absolute z-axis reference. Nothing more than two simple squares. So this is how we could ensure that this upper rail is exactly below the lower rail. You can probably see that from the side. It fits perfectly. We can verify that. Remember, measure twice, build it once. Spirit levels, let's talk about them. Here's the smallest one you'll ever find, a little pocket spirit level. If you put that on something, that's real good, except it can only measure across a span of the length of the spirit level. Get it where it won't fall down from the key ring, right? That's a very, very small degree of angle there. The longer you go, the more accurate you get. See, this one won't quite reach across. It absolutely has to stick, but longer is more accurate. Longer is always more accurate, and longer still. So that bubble should be just about centered if the table's level and this was built correctly, which it was. That's pretty darn good for a welded structure. Haven't even jiggled it to make sure it's sitting square. But you got a nice centered bubble. If you put this on the table, it's centered on the table. So now we have X and Y, and that's how we do that. We found out we can create a Z line with nothing more than two squares. Single square will give you a reference in one plane, but to make sure you don't have any tilt, you have to have this in a pinch. You can do this. You can take a spirit level. You see that? See, as I move it, too far that way, just right. Ta-da! So that's how you get basic measurements. Okay, we got that, but how do we hold this stuff up in the air? Because one reason for a jig is to hold things accurately where they don't wallow around, right? If they wallow around, I guarantee you as you attach these things, it won't be accurate. If I just take two pieces here of metal, put them up there temporarily, stand this one on it, take some kind of square, put it up there, try to line it up. Now the end is not perfectly square, so I'm going to have to try to hold it with my hand, which means it's going to wallow around, or I get a helper to hold it, and then I try to weld that thing. That's not going to be very accurate. We need to hold them mechanically in alignment. So here's how you do that. You need something called stanchions on a jig. So here we can lay out the lower sections in X and Y. Take these wood blocks with screws, create our drawing on the table, make our little dots off our drawing, measure these lines, lay the metal down, and then move wooden blocks up next to them and screw them down through the aluminum cover sheet into the wood below, and that will hold these in firm alignment. very firmly, so they will not move around as you're joining them. Even as the welding is cooling, it will hold them in alignment. So that's what a jig's all about. So that it's obvious that doing the X and Y is simple. Doing the verticals when it becomes trickier. Now I will show you in a few minutes a second way to find Z. But here, this would be a stanchion. Nothing more than a big piece of angle, big piece of steel, holes in it down here so we can attach it to the table. Get the other one. Try to find a place where this will be easily seen. Now, when you bolt these down to the table, you put your spirit level on to ensure that this piece is vertical. You have to double check it with your spirit levels. Now let's assume we've done that. And let's say this rail isn't here yet, and we want to hold that rail up. This is a welding magnetic magnetic holder for material. If you see right here, it has these angles cut on it. It creates a perfect 90-degree angle, and it will stick like so. So we bring this up to the height we want for this plane. Check that with our vertical measurement, Z measurement, lay a rail on it. Do the same thing back over here. Now we can hold the tube in space, and the magnet will hold it suspended, and now we can bring our other members to it. And so that's how you hold things on the second level with these stanchions. They can even be made out of wood. They're just temporary things put in just to hold things until they can initially be fastened. Once they're fastened, then they can be removed and you can use them elsewhere. But it's just that simple. This will create an easily movable vertical magnetic holder that you can move up and down. If you know your height, just bring it up, set your rail on it. That's there. That's all there is to it. That's a vertical stanchion member. But you do have to shim them to make sure they aren't tilted. That's your responsibility on that. Now, let's suppose we've got something we've got to put up that's higher than this will reach. It's not so on this, but let's say there's a big hoop mechanism or something that has to be located way up here. Now, how in the world would we do that? You use what's been used since the time of the pyramids, a plumb bob. You come overhead with any type of structure. Normally I would take two ladders, put a board between the two ladders. From that board, fishing line tied to a plumb bob. That plumb bob, see the sharp point on it? You suspend it. You figure out where your point is on the XY table where something needs to be. Let's just say it's right there. So with this dangling on a string, dangling down, we move the string and the support structure around till this thing is dangling directly above it. Now, anywhere along that string, once it quits swinging, is a perfect Z reference line. So that way we could bring material in, align it off the string that's supporting the plumb bob, and we have a Z reference, whatever height we need. And we can move it easily. Like I say, simple 2 ladders with a board in between them and a simple string of fishing line or small twine. All you need to establish a vertical Z reference as tall as it needs to be. Now, other measurements. What if we don't need a perfect 90 degree? What if we need something in between? You need a protractor. This is just a swinging wheel with degree graduations. So if I wanted to do something like, it's also slightly magnetic. So if you're working off steel structures, so if I needed to establish a certain number of degree angle, let's say 60 degrees, and I wasn't able to use a drafting triangle for whatever reason, Then I just move this up and down till this indicates the proper number of degrees. I come up with some sort of temporary clamp-on structure. Generally, just take C-clamps and spare pieces of metal. And I can come off with an outrigger and move it at any degree I need to be and just clamp on. Whoop! Magnet's not very strong. Simple C-clamp. We'll just rig it up real quick just to show you how easy this is to do. Nothing to it. Clamp it down. Attach your protractor. Put it on the top. Maybe it'll be less likely to fall off. Bump, 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 bump. To whatever angle we decide we need. If we need a 50-degree angle, that's a 50-degree angle. Just that simple. We can also take another clamp, another piece of metal, come up, make a simple triangle so this won't move. Now we could weld it. Just that simple. Simple geometry. Do not overcomplicate these jobs. Try to think of the simplest geometry involved and try to think of a very simple, elegant way to create that geometry and hold it firm enough to where it will not move around on you. Because if I just left that and tried to weld it without the other piece to triangulate it, if I just accidentally went boom, it moved. And if the welder comes along and welds it, it's all off. It's all screwed up just from a simple bump. So what you want to do is find a nice convenient place to come off. Now it's firm. See that? Created a triangle or facsimile. Now this thing won't easily burn. I could weld that, weld it, weld it, weld it, and now it'll be at the angle I need. That's all there is. Keep the geometry simple. Maintain the alignment by clamping force. That's all you got to do. Just that quick, just that simple. But before the final attachment's made, you should always double check the angles and dimensions because things do get bumped. And that's what you have to avoid. You have to be meticulous to the extent that you're double checking yourself, you're checking others around you. Now, can we see these wooden blocks and this structure here? Like I say, here was a simple little truss mechanism that was made. I don't know if you can see it. The pattern for this was actually drawn on this simple piece of plywood. Small plywood blocks were made. The edges were aligned off the drawings. Then the tubes were cut and fitted to where they matched the drawing, and then it was attached. The only difference between this and this is size, and this is in 3 dimensions. This is in only 2. 3 dimensions naturally are more demanding, but they're just as doable as the 2 dimensions. And so that has to do with that. Now, while we're talking about measurements, there's some other tools that a lot of students haven't worked with yet, especially haven't been machinists. Let's say we got a gap. We need to measure a gap. This is called a feeler gauge. It's little fingers of stainless steel. I'm going to fan these out, and they all have different thicknesses. This was 0.011 inch. That's 11 thousandths of an inch. This is 10 thousandths of an inch, and it goes on up through about 35 thousandths of an inch. So if we have a gap, let's say we have a gap between this part and this part, and we want to know exactly what that gap is, but we don't have a way to get anything else. We don't have a way to get anything like a caliper in there. The axis is too hard. This is a caliper. I'll show you it anyway. But when we have gaps and we need to verify spacing or we need to create spacing, we get one of these little bad boys and we just add and subtract these little leaves until we get a thickness that slides in where we want to go. If it won't go in, it's too thick. If it goes in, flops around, it's too loose. You just keep mixing and matches until finally you get just right and it'll just slip right in with you, no problem whatsoever. See? Ta-da, slip right in. 6/1000 of an inch. This is feeler gauges. They come in a lot of use when you're making precision layups and alignments on parts. You won't use them all that often, but when you need them and there's no other way to make a measurement, they're ideal. This is a caliper, vernier caliper. Has a dial on it. A regular vernier only has the scale. You have to read off this mark here as it opens. This is an extra large one. Most of these calipers are 6 inches if they're SAE, or they're 150 millimeter if they're metric. This one is actually twice that. This is my personal one. And if I want to know, if I want to double check the distance between this piece and this piece, then this will open it up. And again, it's all a scale issue. And I can read it off, and these are accurate to plus or minus 1/1000 of an inch. I can read it off this scale, 9 inches. It's 19 thousandths under 10 inches. From the outside of here to outside of here. Another feature, this extends as this opens. This is a depth gauge. Watch as it closes, it retracts. And it goes in flush. So if I want to know how far, let's say this pulley is from this plane, I can set the hilt, crank this thing open, allow the extended rail to go down and touch, and read that off. See, we were only, okay, that should have been right there at 50, so that thing is built to an accuracy of 3/1000 of an inch, which is darn good. Can't beat that. So that gives depth indicator. Now you have jaws. You get a piece of paper so the camera can see this accurately. It's good to know how these jaws actually work them. Here you have very thin tip. This is to get in a narrow opening where you can't get any other way. If you can make your measurements, you want to make your measurements in the center part. This is the squarest, most accurate part. When you go in, you'll notice you have a relief cut here. This is to keep any dirt from getting into the root of the jaw and jamming it open and screwing up the arrow. This is a relief cut. It also comes in handy when you're trying to measure inside. If there is a burr or something like that and you need to reach inside, something like this, and if it's got a mangled up end and it won't allow you to measure it here, you can move it into the relief cut and you have clearance if the end is damaged. Same way with this is an inside measurement. These other jaws are for this is these jaws are measure something on the outside. These jaws measure something on the ID, the inside. I'll get a piece of tubing and show you how these jaws are the mirror image of these jaws. These go on the outside around something. Piece of tubing. They're good for measuring the outside dimension. These jaws are for measuring the inside, and they have that same little relief cut. That's because there's often burrs. When metal is cut, it leaves an edge. So you want to get your jaws past that, and that's what that relief cut's for, so it won't give you a false reading. So the idea of that is 0.906 inch. If you pull this back and try to read that burr, there's a difference. 903. There's a difference in the reading because of the edge burr. So be aware of these relief cuts on these jaws. This is a caliper. It's good for accuracy plus or minus 1/1000th of an inch. Now, there are times because when you need even more accuracy, on something with very, very high quality bearings, something ground of very high precision, you need something called a micrometer. This takes up where that leaves off. This is for accuracy of less than 1/1000th of an inch. Here, this particular micrometer, you notice the C body. This is standard on all micrometers. Here is your spindle. It has a precision ground thread on this thing so that 1 revolution equals 25/1000ths of an inch. So every time it goes around, it's got an index scale as it rotates. It's got a reference line, and it's got another neat feature. Here's your regular knob. See this little tiny knob? This little tiny knob, spring loaded, and it slips. Don't know if you can hear it. It clicks. That's so that as you bring it down and it touches, you turn it not with the big knob, because the big knob you could get a reading depending on just how hard you cranked it down. With this, it allows you to generate the same torque. See, it's slipping now, so those ends have touched, and just the torque allowed by the spring release as this rotates, and you can close these things down and touch and read with the same closing torque every single time. It gives them accuracy of 1/10,000ths of an inch. That's 1 more decimal point accurate than these. 1 order of magnitude more accurate as a micrometer. And you use these mainly on pump shafts, crank shafts, things that require extreme precision. Probably not on this, but definitely on these precision bearings for measuring the holes and everything, because those are built to very high accuracy. These are micrometers. This is a machinist tool. Those of you that have had machine shop training, it's not an issue. You'll be familiar with those. But if you haven't had any machine shop training, then this is a micrometer, and it's for ultra high accuracy measurements. And that's basically the high accuracy tools that we use. So, to reiterate, never work alone. Know where the safety equipment is, first aid kit, telephone, fire extinguishers. Make sure the darn things are charged. And they're got tags on them, because it doesn't do you any good if we have a fire and the fire extinguishers don't work. Create a quality reference plane. Jig your parts accurately and well. That way when you come in here with the welders, we've already had our welding training, you can tack weld. You can actually see the scorch marks on some of these blocks. It's okay to actually weld on these wooden tables as long as you have a fire guard around, because the spot welding doesn't generate enough heat for a long enough period of time to create a problem. Full welding of these joints should not be done on the table. These are just tack welded, then this is lifted off out of the jig, like so. Comes right out of the holding fixture. Then we would either cover this table or move the table out of the way, support it on metal supports to do the final welding. And that's how you create a large structure with jigs, and how to measure it to where it's built accurately. So, there's one thing I really want to show you guys about how to get an absolutely accurate line drawn on any kind of plate like this. It's a nice little trick that I learned years and years and years ago. Use this little piece of plywood here as a stand-in for the tabletop, because there's no use drilling holes in it that we don't have to. Okay, let's take our squares, and I'll put the square on here, get a pencil, and I want to draw a line, let's say 4 inches out from the edge. Make a little cross with a pencil. Come to this edge, make a cross at the 4-inch mark. Now, this is a stand-in for this 8-foot-long table. Let's say we want to draw a center line down this table. How do we do that? Because here's what happens when you start drawing lines. Get a ruler, the right scale, if possible. So let's say we're using a piece of metal, square stock tubing, something like that. We've got our mark, and we line it up to there, and we go to hold it, and we're going to draw it, but what happens is that depending on how I put it to the edge, how my eyeball sees it, plus how well I can hold it down, because as soon as I start drawing, what happens? It generally rotates. It can rotate so easily, and that totally screws up the line in reference to the edge you measured off of. Here's how you do it. You get your little cross, you drill a small hole in the cross as accurately and as centered as possible. Take the drill bit out, turn it upside down, stick it in the hole. This is why I didn't want to drill holes in the table that excessive holes. So this is our stand-in. Come to our other cross that we drew with the pencil as accurately as possible. The smaller the drill bit, the more accurate you will be on dead center. Try to use a big drill bit. It wanders. All drill bits tend to wander a little bit. Stick that drill bit in the hole. Now, doesn't matter if it's an 8-foot table, 10-inch table, slide it up. Trace the line. Absolutely perfect every time. And if you size small drill bits, the line will come out because of the standoff of a pencil or a scribe. A scribe is just a sharp point. I'll just drag a line in the metal. It will come out dead center on the hole. Doesn't get any better than that. I don't know if you can see it, but the line lines up perfect on the hole. And that's how you can create a perfect center line on your table or a perfect reference line in either X or Y. Nothing to it. That's it.